Whether you're installing a projector in a boardroom or setting up a touring rig, understanding electrical systems is essential to being safe and competent AV professional. In this video, we'll walk through the fundamental concepts of electrical power in Pro AV systems, from the way current flows to how circuits are structured to how we design for safety. We'll cover the basics of voltage, current, and power, circuit types, AV power distribution, grounding and safety, and temporary versus fixed install best practices. Let's start with the very foundation, voltage and current. Voltage is the electrical potential difference between 2 points. You can think of it as electrical pressure, the push that causes electrons to move through a conductor. Current, on the other hand, is the flow of those electrons. It's what actually moves through the wires and powers your gear. Voltage is measured in volts, simply symbolized as V, and current is measured in amps, symbolized as A. And there are 2 types of electrical current you will work with. Direct current, or DC. It flows in one direction. It's what powers most electronics, including your laptop, media servers, and digital processors, for example. The other type is the alternating current, or AC. It rapidly switches direction. In North America, that's 60 times per second or 60 hertz. AC is what comes from the wall outlet, and it powers amplifiers, projectors, displays, almost all your big hardware. As an AV technician, it's crucial to understand this distinction. AC comes in at the wall, but inside most gear, it's converted to DC. That's why power supplies and transformers matter. Now that we've covered those basics, let's talk about what resists current, resistance, and impedance. Resistance opposes DC current and is measured in ohms. You typically see it symbolized by the Greek letter omega. Impedance is the total opposition to current in AC circuits, and it includes resistance plus a frequency-dependent component called reactance. This is where Ohm's law comes in. One of the most important relationships in all of electronics. Here is the takeaway from this. If voltage goes up and resistance stays the same, current goes up too. And if resistance goes up, the current goes down. Let's unpack this a bit more. Let's talk about power. In the context of our industry, power is the rate of doing electrical work. In our case, it is how much energy we are using or producing in an AV system. The formula is simple. Power equals current times voltage. The result is measured in watts. So if a projector draws 5 amps at 120, that means power equals 5 times 120 equals 600 watts. Knowing this helps you plan load capacity, choosing outlets, and avoid circuit overload, especially when managing high-powered gear like LED walls or powered speakers. So now that you understand the basics of voltage and current, let's take a closer look at how electricity actually flows and what might get in its way. Electric current is simply the flow of electrons through a conductor, usually a wire, from one side of a power source through the circuit and back again. You could think of it like water flowing through a pipe. It starts at the pump, moves through the plumbing, and returns to the pump. Now, in the real world, electricity doesn't always flow a perfect path. Current will flow through any available conducting path, not just the one you designed, and it will favor the path of least resistance. When electricity finds a shortcut, say a wire accidentally touching another or an exposed conductor. This is what is called a short circuit. It bypasses the intended load entirely and can cause dangerous levels of current flow. And if a person becomes part of that path, you now have an electric shock hazard. How dangerous it is depends on how much voltage is present and the resistance of the person's body, especially if the skin is wet or broken. Let's unpack resistance a little bit. Recall that we said resistance is what limits current flow. It is like friction in an electrical system. It's measured in ohms and represented by omega. Materials like copper and silver have very low resistance, which is why we often use them for wiring. On the flip side, rubber or air have high resistance, and that's why they are used as insulators. The longer a wire, the more resistance it adds. The thicker it is, the less resistance it has. So when planning a system, longer cable runs or thinner wires increase resistance, and that can cause voltage drop. Resistance isn't the whole story. In AC systems, there is another factor we have to think about: impedance. Think of that as the total opposition to current flow. It includes resistance plus reactance. Reactance is how components resist changes or in voltage or current. It is made up of two types: inductive reactance from coils, transformers, and capacitive reactance from capacitors and signal cables. The key difference is that resistance affects DC and AC equally. Impedance only matters with AC, and that includes audio signals, video signals, and power in AV systems. Understanding resistance and impedance is critical when sizing cables, choosing amps, or troubleshooting why a signal gets distorted over long runs. Too much impedance and your signal might never make it to the other end and get distorted along the way. So we've explored voltage, current, and resistance and how they interact in a circuit. Let's take a look at how these values translate into power and how you can use Ohm's law to design and troubleshoot AV systems with confidence. Recall that power is measured in watts. In electrical systems, it's calculated using the core formula of power equals current times voltage. So if a device draws 2 amps at 120, it uses 240 watts. And with Ohm's law, voltage equals current times resistance. So if you know any two of these values, you can always solve for the third. Let's say you have a 12-volt power supply, and your speaker has a resistance of 6 ohms. You can calculate the current as I equals V over R, which is 12 over 6 equals 2 amps. Once you know the current, you can plug it back into the power equation, and that gives you 24 watts. By combining Ohm's and power law, we get a powerful toolkit for designing circuits and selecting equipment. Here are the most useful combinations. If you want to know voltage and resistance, you can use P equals V squared over R. If you want to know current and resistance, then P equals I squared times R. If you want to solve for voltage when you know power and resistance, it's the square root of P times R. These variations are especially useful when sizing cabling, planning power budgets, or designing audio systems where impedance matters. You might be asking yourself how this shows up in the real world. Let's say you're powering multiple LED screens or speakers on a single circuit. You need to know how much total power they'll draw and whether the circuit can handle the current and what size wire you need to avoid voltage drop. Maybe you are troubleshooting why an amplifier is cutting out. You suspect the speaker load is too low and drawing more current than the amp can deliver. Using Ohm's law, you can check. So it's I equals V over R. And if the resistance or impedance in this case is lower than expected, current is increasing, possibly tripping a protection circuit. Every AV device that uses electricity needs to be part of a circuit. That means there must be a complete path from the power source through the device and back again. You can think of this like a racetrack. The electricity can only flow if there is a loop, a return path. If there is a break, the race is over. That's the basic idea of a closed circuit. So, what makes up a circuit? In its most basic form, a circuit includes a power source like an AC outlet or a battery, one or more loads, the device that consumes power, like displays, speakers, or processors, conductors, the wires or cables that connect them, and possibly a switch or controller to start and stop the flow. In AV systems, things are more complex with multiple sources and multiple loads, sometimes spread across rooms or buildings. But no matter how big the system, all circuits are built from two connection types, series and parallel. In a series circuit, current flows through every component, one after the other. That means there is only one path for the current. All devices share the same current. Voltage is divided across each load. So if one component fails or is disconnected, the whole circuit breaks. In power distribution specifically, this is rarely used. It's too fragile, but you will sometimes see serious wiring in signal chains or maybe legacy control wiring. On the other hand, a parallel circuit connects every device directly to the same voltage source. This is how almost all AV power and signal systems are wired. That means that all loads receive the same voltage. Current is split between paths based on resistance. So if one device fails, others keep working. This approach gives you more reliability, better power regulation, and simpler maintenance. Let's take a practical example into account. If you're wiring 4 amplifiers into a rack, all powered by the same circuit, if they were wired in series, they would each receive only a portion of the voltage. On the other hand, if they are wired in parallel, they each get full voltage, and the circuit breaker just needs to handle the total current draw. This is why load balancing matters. You calculate current for each parallel branch and make sure the circuit can handle the sum of those loads. Grounding or earthing is the practice of connecting the metallic parts of equipment to the earth itself. Why is that? So this happens so that in the event of a fault, say a live wire touches a metal chassis, the current has a safe path to follow and away from the user. Without this grounding practice, that current might travel through the next person who touches it. Effectively, grounding protects lives. Pro AV systems, we typically ground equipment chassis, rack frames, metal faceplates, power conduits, and mounting structures. This is especially important in mobile systems, stage setups, or any environment where equipment is handled frequently. Proper grounding allows circuit breakers to detect faults and shut off power before harm is done. You've probably encountered ground fault circuit interrupters or RCDs. These are fast-acting safety switches. They monitor how much current flows into and out of a circuit. If there is a mismatch, say electricity is leaking to ground, they shut everything down in under a tenth of a second. These devices are mandatory in many jurisdictions, especially in wet areas, temporary installs, or outdoor events. But not all devices need to be grounded. Some are built with 2 layers of insulation and have no exposed metal parts. These are often called Class 2 or double insulated devices. They are safe to use without grounding because there is no path for a fault to reach the user. You'll see this in things like phone chargers, small speakers, and lightweight control surfaces. Still, always check the label and never remove the ground pin from a plug, even if the device seems safe. Even in well-grounded systems, there is another challenge: ground loops. A ground loop happens when different parts of your system are connected to slightly different ground potentials. The result is buzzing or hum in your audio, shaky or drifting images in your video, or some sort of mysterious system instability. To prevent this, AV systems often use isolated grounds, where sensitive devices are all bonded to a single grounding point that then connects to Earth. This minimizes differences in potential and helps eliminate noise. Many AV systems use a technical power setup or a dedicated isolated ground electrical supply used only for AV and IT equipment. This reduces interference from high noise devices like vacuum cleaners, power tools, coffee makers, and fluorescent. When you're out in the field, mark these outlets clearly, and when possible, use color-coded faceplates to avoid these mistakes. So to summarize this, whether you're working on a permanent install or a temporary live production setup, here are a few ground rules to take into account. When it comes to fixed installations, use correct grounding techniques. Don't exceed conduit fill limits. Label Pro AV only circuits and install proper overload protection and GFCIs. Ensure access to shut-off switches. In live production setups, test all power sources before plugging in. Inspect every cable one more time. Use the right cable gauge and length. Avoid overloading your circuits and keep outdoor gear weather resistant. And protect cables with covers and secure them safely. Remember that grounding protects users and systems from dangerous fault currents. Using interrupters or RCDs is important to detect faults and cut power instantly. Double insulated gear doesn't need grounding, but it must be used as specified. And isolated ground systems prevent noise and hum in Pro AV installations, and never ever bypass grounding. It's not just bad practice, it's unsafe. If you remember one thing from this section, let it be that electricity does not forgive mistakes. So as you design, do that with safety in mind. Follow codes and communicate clearly with electricians and facility managers. Here is what we covered in this video. We covered the fundamental concepts of electrical power in Pro AV systems, from the way current flows to how circuits are structured to how we design for safety. Current and power, circuit types, AV power distribution, grounding and safety, and temporary versus fixed install best practices. That's it. Thanks for watching.